We're going to take a look at marginals and differentials. Same basic idea. You'll see what I mean when we get through this. But we're going to take a look at marginals first. Let's take a look at the idea in the business world, so to speak. Let's say that we have some cost function here. Now this is the cost when we produce X items. Let's call them bikes. So if I make 20 bikes and we plug it into this formula, that would give me the cost for making 20 of them. So here's our cost function, but let's say we don't actually know exactly what that function is, but we do know, since I said 20, let's say we do know the cost of making 20 bikes. And for right now, let's say that's $1,000. I'm going to change that notation here in a second. So if we make 20 bikes, they cost us $1,000. Now the question is, how much would it be to make 21 bikes? Well, we can figure that out using the tangent line a little bit, at least get close to it. So let's say over here at 20, we wrote we drew the tangent line to the graph here. Now I know the slope of this line is the derivative, so this would be c prime of x. Now remember, that's our rise over our run. Well, if we're trying to figure out what that value is there, the cost for 21 bikes, the run here was only 1, so you can kind of think about this as a c prime of x over 1. So from going from here to here, our run was 1, so I'm going to kind of just go over like this. So the distance from the tangent line down to here, that's our rise, so that's c prime of x, right? Rise over run. So we have this value here. So if I want to approximate this, which would be c of 21, well, what's c of 21 pretty close to? Well, let's see, c of 21 is approximately equal to, well, that would be c at 20. Remember, this is what I called the 1,000 here, just made it up, c of 20. c of 20, that's this distance here, c of 20 plus c prime at that same spot. So that'd be c prime at 21. So this will be c of 20 plus, well, remember this right here, this was our derivative at 20. So this is actually c prime at 20. I'm going to put the 20 in there, right? Because that's the slope of the line over here. So it'll be at c prime of 20. So if I wanted to know the cost for making the 21st bicycle, I could approximate that by using the cost of the 20th bike, which I would know, and the derivative of the cost at the 20th bike. Now what this actually gives us, if we rearrange this a little bit, we can see that c prime of 20 would be equal to, let's move this over. That's be c approximately c prime of 21 minus c of 20. Now, what would this actually give us? Now, think about what this over here is saying. This is the cost of making 21 bikes. So this is the cost of making 20 bikes. So if you take the cost of 21 bikes and you subtract off the cost of 20 bikes, what you actually get is this is the cost for making the 21st bike. So the cost for making x plus 1 items is approximately equal to the derivative at the last item. So you just kind of get this weird little approximation here. Now, so if they were saying approximate the cost or find the cost of making the 50th bicycle, all you'd have to do is take the derivative and evaluate it at that spot. All right, I'm back. Sorry, the video cut funny there. So we were talking about finding the marginal cost of something. Now, in terms of this course, anytime you hear the word marginal, you're thinking the derivative. So we can use the word marginal with any of our kind of business terms. So as we just saw a second ago, the marginal cost is really just c prime of x. Marginal, let's see, profit would be p prime of x, and marginal revenue is R prime of X. So you hear the word marginal, all you're doing is you're thinking of the derivative. So let's take a look at an example of how one of these might be worded. So let's say I gave you two functions. So let's say I said R of X was, I don't know, 50x minus 1/2 x squared. And see, I'm cheating, I'm copying one. Let's see, we got C of X is, let's do 4x plus 10. All right, so here we have a revenue function and a cost function. Let's see if we can answer a few questions. Let's see, first thing, let's see if we can find the profit. That one should be straightforward. Step 2, let's see if we can find, I don't know, our revenue if we make, by the way, remember, this is the revenue for making X things and the cost. So the revenue if we make 10 things, cost if we make 10 things, and profit if we make 10 things. Let's see. 3, what else might we want to do? What about if I ask you to find R prime of X, C prime of X, and P prime of X? Now another way of wording this is, what's the marginal revenue, marginal cost, and marginal profit? And the last thing, what about R prime of 10, C prime of 10, and P prime of 10? Let's see how this works out. All right, so we've got a lot of work to do here. Let's start out with the easy one. First off, we're told to just find our profit function. So we know our profit function is the cost function minus it's our revenue function minus our cost function. So for our profit, let's go ahead and figure that out. Our revenue was 50x minus 1/2 x squared, minus our cost is 4x plus 10. So P of X, I'm gonna put this in descending order. Negative 1/2 x squared, 50x minus 4x would be 46x minus 10. Okay, so there's our profit function. So we have our revenue, our cost, and our profit. So that answers question 1 for us. Question 2 is just a bunch of arithmetic. We're just going to take 10 and plug it into all of these functions. So our first one, R of 10, we're plugging into our revenue. So that's 50 times 10 minus 1/2 10 squared. So really quick, that would be 500 minus 1/2 of 100. So skipping a step, half of 100 is 50, so this will be 450. So our revenue, if we make 10, whatever these things are, will be $450. C of 10 will be 4 times 10 plus 10. So it would be 40 plus 10 would be 50. And our profit, if we make 10, should be, let's see, let's plug it in here. It's going to be negative 1/2 10 squared plus 46 times 10 minus 10. So again, that's going to be half of 100. So it's negative 50 plus 460 minus 10, which should be 400. Now, we should have already known the answer to this just by looking at it. I just wanted to show you that it worked right. We know the profit is revenue minus cost. Our revenue was 450, our cost was 50, so 450 minus 50 is 400. All right, so let's get into the few things that we were taking a look at today, kind of the marginal stuff, which is really just the derivative. So the derivative of all three of our functions, let's do revenue first. R prime of X is just going to be 50 minus X. Right? I'm just taking the derivative of this, just bring down the power, take one away from the power. What was next? C prime of X is going to be the derivative of our cost function, that's just 4, and P prime of X, here's our profit function, that's negative X plus 46. Okay, those should be pretty easy derivatives for us by now. Let's answer our last question. Our last question is take all three of those functions and evaluate them at 10, and we'll see what that actually means for us right here. So r prime of 10 is going to be 50 minus 10, which is 40. C prime at 10 will be, well, 4. And P prime at 10 will be negative 10 plus 46, which is 36. Okay, so what is this telling us? Well, it says R prime of 10, or the marginal revenue. Remember, the marginal revenue generally tells you about the next item. So R prime of 10 is actually talking about the 11th thing that we would have sold. So how much revenue will we make off of the 11th, whatever these are? Well, we would make $40. What would the marginal cost be? Well, notice the marginal cost here is a constant, which means in this case, it doesn't matter how many we make, it's always going to cost us $4. So the 11th thing will cost us $4, or the 12th, the 100th, or whatever, because it's a constant. The profit for the 11th, remember the next one, would be $36. Now notice, this is actually going to go down a little bit here, because our revenue is also going down with the more and more that we sell. Okay, so marginal just means the derivative. And anytime you're talking about like the marginal revenue, cost, or profit, you're talking about the next item in the that you're producing or selling or creating. Now, another way that we can kind of use the same idea is something called differentials. These are very, very closely related if you kind of get the idea here. All right, so we know from the past, let's just do this, from a long time ago, y2 minus y1 all over x2 minus x1. That was the slope of a line, any given line. And another way that we could write this is that's the change in y over the change in x is equal to m. Now, think about this in terms of fractions. If I were to multiply both sides by delta x here, I can see a change in y is equal to the slope times the change in x. So basically the idea here is if we were looking at some graph, and it's going to look a heck of a lot like the picture I just had up here. If we're looking at some spot, and I move over a little bit, right, x plus a small change in x, the idea here is how much does this change here? That's the change in y. Well, that change in y is going to be the slope times the change in the x. Well, if we were to put this in terms of our calculus stuff that we've done, and like I said, it's going to look a heck of a lot like our last picture. If this is our function f, and that's the slope of the tangent line here, then the slope of this line right here is f prime of x. So we could say that a small change in y is f prime of x, x. Now, this ends up just being an approximation. Well, this is exact. But the idea here is, could we figure out if we make a small change in x, what does that do to this y value? Well, the pictures ends up being exactly the same as what we did before. If I want to know what that is right there, if I want to know what f of x plus delta x is, well, that's going to approximately equal to, well, think about what we did here. I'm looking for this value. I know that this change from there to there is delta y, right? So we would have our original function here. This y value is f of x plus that little change in y. So this would be f of x plus that change in y. Remember, the change in y is the distance from there to there. That's our slope. Well, we saw from a second ago that our change in y can be written as f prime of x dx. So f of x plus delta x is f of x plus f prime of x delta x. Okay, so if we're looking for just a small change here, we're saying if we move over just a little bit, then we can approximate that using our slope, because the slope of the tangent line is generally going to be fairly close as long as we don't move too far away. All right, so another way to think about this is a new way to kind of take a derivative, and we'll see how we can use this idea here in a second to approximate some functions. But here's another idea. We saw in the past that dy dx was f prime of x. Right, those are just our two different notations. Now notice, this looks almost exactly like what I had on the board a second ago, right? Change in y over the change in x is equal to m, right? The change in y, dy, over the change in x, dx is the slope. Same exact thing, which means I can say that dy is f prime of x dx. Now, this is just another way to write a derivative, and this is called the derivative in differential form. Now, the reason that this is useful is this, we'll get back to that in a second, is if you think about our chain rule. Remember when we first saw our chain rule, we had something like this. I said, find the derivative with respect to x of, I'm just going to say u to the n. Now here, remember, we're assuming that u is some function of x. And we said, well, we use our power rule like we always do, bring down the power, take one away from the power, but then we have to multiply by the derivative of the inside. Now, we were writing u prime here, but remember, I'm going to change that now just to du. That still just means the derivative of u. Now, in this case, since we're using our chain rule, if I said u was a function of x, this would actually be du dx, right? Because I got to take the derivative of the inside with respect to x. However, if let's say u is a function of t, then that would be du dt, right? If f was a function of m, this would be du dm. So a more generic way to write this is just, let's assume that u is some function of some other letter and just write the derivative of u with respect to whatever letter it happens to be. So in this case, that's kind of what we're doing. We're taking an all-purpose derivative. We're saying that here, x and y can both be a function of some other letter. So notice I could say, well, what if they were functions of t? I could say dy dt is equal to f prime of x dx dt. Or if x's and y's were functions of other letters, we could change this, but the only thing that would change would be this, like it would be dy dm. So generically speaking, we can just say, hey, let's just call it the derivative, and whatever letter's the independent variable, it doesn't matter. Now, being able to take a derivative this way is going to be very important in chapters coming up. So let's just take a few examples of this. The good news is our rules don't change at all. So if I said, find the derivative in differential form, and let's see, I have y is equal to x squared plus 3x plus 2. All right, now on this side, we generally would have written something like maybe y prime. Well, all that means is that's the derivative of y, so we're really just changing our notation here a little bit. So I'm going to call that dy, the derivative of y, equals the derivative of x squared is 2x times the derivative of x, which is dx, plus the derivative of 3x, which is 3, with respect to x, which is dx. And the derivative of 2 is 0 dx also, but that's just going to be 0. So there's our derivative in differential form. Here's a quick way to think about it. Anytime you take the derivative of a variable, you always get the derivative of that variable tacked on. Now, the way that we're generally going to write this in the future is we're just going to say that's 2x plus 3 dx. And to be honest, we're going to get super lazy in the future. Don't write this down in your notes yet. We're going to say dy is, this is horrible, 2x plus 3, and just put the dx. I know you can barely see that. Put the dx all the way on the outside and kind of forget the parentheses. But really that dx applies to all of that. We'll see that a little bit later on. So notice here, there's really no new rules in taking derivatives. Just anytime you take the derivative of a letter, you get the derivative of that letter next to it. So let's try one of these here real quick. Let's say we have y is equal to x squared e to the x plus the natural log of x. All right, hit pause and see if you can take this derivative in differential form. All right, you're back. Let's see how you did here. So the derivative of y is just, well, the derivative of y, dy. Now for this first piece, we do need to do our product rule. So the derivative of 2x is going to be 2x. Technically the derivative is 2x dx, right? But then times e to the x, so I'm just going to put the dx on the end. Plus, and then we're going to take the derivative of e to the x. The derivative of e to the x will be e to the x dx, but we have the x squared there, so it'll be x squared e to the x dx. And the derivative of a logarithm is 1 over the argument times the derivative of that argument. Okay, so there's your answer. There's your derivative in differential form. So again, our rules haven't changed at all. The only thing that we're doing now when we do this is we add the differential piece after we take each derivative. Now, what is all this good for? Well, we're really going to see how this is useful next chapter when we get into something called integration. But we can also use what we had on the board a second ago, that f of x plus a little bit is approximately equal to f of x plus f prime of x delta x. Now, what do we mean by this? Well, what if I asked you to approximate the square root of, I don't know, 18? Now, that is something you should be able to do off the top of your head fairly quick, right? That's really close to the square root of 16, so it's really close to 4, and you should be able to get kind of close. But here's what we're going to do. Since the main function here is the square root, we can actually get really close by doing this. Let's say that our function here is just the square root of x. Now, we're going to use this formula on this side, so you notice we need the derivative of this. So if f of x is x to the 1/2, f prime of x would be bring down the power, take 1 away from the power. Now I'm going to just simplify how that looks. It's 1 over 2 square roots of x, right? The negative exponent takes it to the bottom, and that 1/2 power is the square root again. Okay, so here's the idea. You say, I don't know what the square root of 18 is, but that's really close to the square root of 16. So that's 16 plus a little bit. So here what we're going to do is we're going to say, let's let our x be something we know, and then our change is how much we're away from that. So by doing that, I can say that there's our function, the square root of 18, so square root of 18, is approximately equal to f at x, which is 16, plus f prime at, f prime at 16 times our change in x, right? So f at 16 plus f prime at 16 times how far we moved away. Okay, so the square root of 18 is approximately, well, our function f was the square root, so it's going to be about the square root of 16 plus 1 over 2 square roots of 16 times 2. So the square root of 18 is approximately equal to, well, square root of 16 is 4, plus the 2 and the 1/2 cancel, so that's 1/4. So the square root of 18 is approximately equal to 4 1/4, which in this case is 4.25. All right, so as you're sitting there, do me a favor, grab yourself a calculator and see how close that actually is. You're actually going to be surprised that it's really, really close to that answer. So we can use these differentials to approximate functions to where we know the function value at a specific point, but we've moved away from that a little bit and we just want to know what is it really close to. So marginals is what we started this lecture at. Remember, just means the derivative of that function, and it tells you the value of the original function for the next item. And differentials is just a new way to take a look at a derivative. Notice it's a lot of the same ideas, and we can use it to approximate the value of functions when we know a specific spot, when we just want to move away from it just a little bit.